Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study Mcallist method, part 1. So far, we have covered various methods such as double integration method, we have covered. And double integration method, double integration method is suitable for certain problems we can solve very easily. But this Mcallist method is highly useful for solving the problems of eccentric load of a simply supported beam. We have seen in double integration method, in the case of a simply supported beam with an eccentric load, it was we observed that the complexity is more complicated by using double integration method to find the slope and deflection along the length of the beam. But in order to, this Mcallist method is very simple, and also it can be understood easily for any type of, for the problems of eccentric loads and uniformly distributed load, and also combination of point load and uniformly distribution load to find slope and deflections along the length of the beam. Now, what is Mcallist method? Here, the Macaulay is the name of the person who devised this method. That's why this method is known as Mcallist method. Actually, this method mainly consists in the special manner in which the bending moment at any section is expressed, and we can carry the integration can be carried out. Now here, the case we consider for explaining the Mcallist method is here simply supported beam is having with an eccentric point load, and having the length of the beam is capital L and supports A and B. The eccentric load is acting at a distance of A from left support and B from right support from my side. Now here the reactions are calculated by using the concepts of shear force and bending moment diagrams. So here we found the reactions at A and B. The reaction at A is WB by L, and reactions at B is W times A by L. Now we know the equation at the bending moment at any section X, that is Mx equal to Ra times X, that is WB by L times X. We know the Ra, that is the value of the Ra is WB by L. After substituting at the place of Ra, reaction at A, that is WB by L times X. Now, this equation for values of X between 0 and A, if you want between from point A to C, but if you want between C and B, the bending moment that C and B at a distance X. Now, the distance is at a distance of X. So how to apply the bending moment here? The bending moment equation for a distance, this is the bending moment equation for a distance A to C. We want the distance from C to B. What is at now X is at between C and B. Now the bending moment at a distance of X is Ra times X minus W times X minus A. Now what is the Ra here? WB by L times X minus W times X minus A, Mx. Now this equation is good for all the values of X equal to A and X equal to B. This equation is only for the portion of between the variation of the slope or bending moment from capital A to C. But the equation we derive now, second equation, that is the equation, this equation can be useful for when X equal to A and X equal to B. Now what we are going to do in this method that make a divide, we are making a dotted lines for sections. This equation is suitable for throughout the section. So we are going to make into a single two parts, we are going to make a partition. This part Mx equal to WB by L times X is suitable for the distance of variation of the slope and deflection between A and C. and a total sum, the two parts is combination mx equal to wb by L times x minus w times x minus a is useful for throughout the span of the beam. Now, this is the two parts we made here. Okay, this part, first part is for up to A and C, between A to C, and combination of first part and second part is up to from point A to B. Now, this is the equation. We are going to do it. Now, we are using it. Now, we know the equation of mx at any section, that is ei times d square by dx square. Yeah, this is m equal to ei times d square y by dx square. So, by equating 1 and 2, that is whereas mx and this m equation, then the equation is transformed into equation 3 as ei times d square y by dx square equal to wb by L times x minus w times x minus a. Now, this is the equation we are going to integrate. First integration gives a slope, and integrating the slope equation gives a deflection. Now, this is we'll discuss more how later on after completion of this Mcallist method procedure, then we can understand how what is the relation between Mcallist method and double integration method. Now here first integration, integrating the equation 3, that is ei times dy by dx equal to, now we are going to use this constant of integration in the first part only we are going to add, not in the second part. Now wb by L times x square by 2 plus c1 minus w times x minus a whole square by 2. This is equation 4. This equation 4 gives the deflection slope equation, provided if we know the constant of integration c1 is known. Now what next? Now after the c1 is known, next if we integrate the equation 4 again, second one more integration, then it gives deflection. The deflection is that ei times y equal to wb by 2l x cube by 3 plus c1 x plus c2 is minus w by 2 x minus a whole cube by 3. This is the transformed, the equation 4 is transformed into equation 5. That equation 5 is known as the deflection equation, provided the c1, c2 constant of integrations are known. So, the c1 and c2 are constant of integrations. How to find out constant of integrations? By using boundary conditions. If you want two constants of integrations, that means we need two boundary conditions. Alright. Now, let us use the two boundary conditions. The two boundary conditions are at x equal to 0 and y equal to 0. At x equal to 0 means the length of the beam is 0. Y equal to 0, the deflection equal to 0. Y stand for here deflection. It is not x and y coordinates here. Y for deflection, x for the length of the beam, span of the beam. Now what is the second boundary condition? At x equal to L, at a distance of L, what is the slope? What is the deflection? 0. That means at supports at x equal to 0, y equal to 0, that means it is the support A. And x equal to L, that is support B. What is the deflection? 0. So by using these two boundary conditions and substitute wherever in, so it is related to deflection equation, so we have to substitute these two boundary conditions in a deflection equation, that is at A, x equal to 0 and y equal to 0. What is the deflection equation is here? Equation number 5. This is the deflection equation. In this equation, you will substitute two boundary conditions. Okay, at x equal to 0, y equal to 0, after substituting the first boundary condition, the observed value is constant of integration c2 equal to 0. At b, x equal to L and y equal to 0, substitute again back. And c2 also substitute. C2 we got 0. And x equal in the place of x, substitute as L and y equal to 0. Then the c1 is obtained. What is the c1 value? Minus wb by 6l times l square minus b square. This l square minus b square c1. And what is the next? c2. These two you substitute. If you substitute in both deflection equation and slope equations, then you will get it. the generic or parametric slope and deflection equations. Now, substituting C1 value in equation 4, that is the slope equation, then EI times dy by dx equal, this is the equation, we got it. Next, what is the deflection equation? The slope, this is the slope equation. Now, if you want a slope maximum value at A or B, then what is x equal to 0? If you substitute x equal to 0 in equation 7, we will get slope at supports A. If you substitute x equal to L, we will get where? The slope at support B. Now here we are doing x equal to 0. Now the equation becomes, substitute here WB times 0 by 2L, that is 0 minus WB times by 6L, L square minus B square. Here x equal to 0 minus into minus, that is plus W. Here minus A square means plus, minus WA square by 2. So after simplification, we will get the equation. Oh, what we want, one thing very important point is here. Here we want x equal to 0 substitute in which part? This x equal to 0 in the first part. There are two parts are there. This is the first part up to the variation of the slope between A to C, point A to point C. Combination of the total is connected to A to support B. Now x equal to 0 support A is related to first part. So in the first part, if we substitute x equal to 0, then EI times theta A equal to WB by WB by 2L times 0, that is 0, minus WB by 6L, L square minus B square. This is the equation. At support A, theta A equal to minus WB by 6EIL times L square minus B square. Alright, this is the support at A. Next, we want a deflection. Yes, this is the deflection. After getting deflection, that is I times y equal to WB by 6L x cube plus minus WB by 6L L square minus B square times x plus 0. This is the equation. Now we want a slope, or we want a deflection at point C, where the load is acting. So where is which part we have to consider? We have to consider the first part. So in the first part, what is x equal to A? Substitute x equal to A, that is WB by 6L, x equal to A, that is A cube, minus WB by 6L, L square minus B square times x. What is that x equal to A? That is simplification. What will happen here? WB by 6L. What we are going to do here, make it a common, A common. Then what will happen? It is A square minus L square plus B square. This is the equation. Now further simplification, WA minus negative of WAB by 6L. Then what will happen? L square minus A square minus B square. Now we know that further simplification, what we are doing, we know L, total span L equal to A plus B, distance, sum of the distance A and B. Substitute in the place of L, that is A plus B whole square. This is A plus B whole square minus A square minus B square. So minus negative of WAB by 6L, what is A plus B whole square? Simplify A square plus B square plus 2AB. This is minus A square B square. Positive, negative term, negative and positive term will be cancelled, both A square and B square. Then what will happen? What is left here? W time minus negative of WAB by 6L times 2AB. Then what will happen? 2 get cancelled 3 times. So W A square B square by 3L. Now that is EI times YC. We want YC, that YC equal to W A square B square by 3EIL. This is the deflection at applied load. It's so simple how we are getting here directly. This is the same as before by using direct double integration method. That is the deflection. Now in this equation 7, if you substitute x equal to L, that gives the slope at B, support B. Total equation we consider, part 1 and part 2 both. Okay. Now how it comes here, part 1 and part 2 if we consider, what is the slope equation? That support at A, slope at A at B. we want slope at B. Slope at B, that is EI times dy by dx at B, then what to substitute here? X equal to L, because that is the total portion. In the total portion, both the parts, WB x equal to L square by 2L minus WB by 6L times L square minus B square, negative term W times L minus A whole square by 2. Now, yes, L get cancelled here. WB L by 2 minus WB by 6L of L square minus B square minus W by 2 L minus A whole square. So if we simplify further, I'm going to write down here. Yes. So make it common here, WB by 6L, and make it LCM and calculate. Then this is the equation will be obtained. That is WB by 6EIL times L square minus B square. It will be obtained here. If we simplify it, that means if we simplify it, it will not be obtained, because here the load is eccentric load. Eccentric load. So it will be definitely, we can see the slope at B. Slope at B can be calculated if we simplify. This is the in terms of yes, it is in terms of length and the width, the support left from the eccentric load acting from both left support and right support over the simple supported beam. Okay, this is the Mcallist method. We calculated here in this Mcallist method, especially we derived what is the slope at A and also the deflection at load is acting. So the deflection at load is, that is the YC, that is W is negative of W S square B square by 3I times L. What is the difference between, now we have a question that what is the difference between Macroless method and double integration method? Here in Macroless method, we also use double integration, 2 times integration. But here, but whereas in the double integration method, there is no partitions. So in order to find out for the case of eccentric load, so what to be considered, we have to do it 2 times. Double integration method, we have to use it 2 times in order to get the deflection at the load where point C is acting, that is eccentric load is acting, that point. But whereas in Mcallist method, it is so easy that directly obtained wherever we want. The way we made it here, the Macaulay is so simplified that we consider 2 parts, wherever part 1 means up to the point, up to the load where is acting, and after the load. So these 2 deflection equation are bending moment equation, and we made a dotted line as a partition. That means that first part is related to up to the eccentric load, and combination of 2 parts related to up to throughout the span of the beam. And where that throughout the span of the beam, we have to integrate first integration and second integration. That's why this Macallist method can be useful for all types of problems. We can solve very easily, and we will see in the coming sessions. So you can feel it that is so easy. But the methodology for Macallist method is, you have to take the equation, bending moment equation, consider the length of a span of the beam such a way that in that equation throughout all loads will be included. Okay. Otherwise, what will happen? You cannot, there also flaws are there. If you don't get that equation, if you cannot apply for throughout the span of the beam. So we have to consider the section of the beam such a way that that equation involves the bending moment, the effect of bending moment, deflection and slope can be calculated throughout the span of the beam. As we have considered here, what is that meaning here? Let me explain here. Simple. Yeah, here equation 1 and equation 2. Equation 1, mx equal to Ra times x, that is Wb by L times x. Up to what distance? We considered the x distance. We consider the x distance between below the point C, that is between A and C. But we want throughout the span of the beam. Then the second equation, how we made it? Now x is shifted to between C and B. Between C and B. Now this equation involves the variation of the bending moment throughout the span of the beam. That is the mx equation. This equation involves. Okay, now this equation involves the first part, equation 1, that is Wb by L times x, and also negative value of W times x minus A. So this first part integration up to first part considers between A and C, A to C, and sum of first and second parts involves the variation of bending moment from A to B. That's why we consider the second part. And that equated this second part to the equation at any section, that is Ei times d square y by dx square. That Ei times d square y by dx square equal to Wb by L times x minus of Wx minus A. Alright, in that manner, now if we, now after getting this equation, now this is the equation. If we integrate first integration, it gives slope. Integrating the second equation gives deflection. But again, which portion you want? Between A and C, A to C, variation of the slope and deflection. If you want to find out the value of slope and deflection between points A to C, between points A to C, what to do? Between points A to C, which part we have to consider? We have to consider part 1. This is the part 1 and part 2. And if you want to variation or the value of slope and deflection between C and B, then what to consider? The two parts, sum of part 1, the total equation are to be considered, provided constant of integration are to be known. Alright. So that's why this Mcallist method is so and highly useful and very easy in comparison to the double integration method. Now, how much it is easy, let us go for. Here there is no, for this variation, different problems, different point loads at different distances. First we have to find out the bending moment equation at any section. Next, that equation should be, we have to integrate first. First integration gives the slope. Second integration gives the deflection. The deflection equation consists of two constants of integrations. Those two constants of integrations can be calculated by using two boundary conditions. After calculating those two constants of integration, you have to substitute back in slope equation and deflection equation. And those equations are parametric equations, or that are generic equations. In those equations, if you substitute the x from 0 to the span of the length L, then you can vary, then we will get the slope and deflections throughout the span of the beam. Now, let us apply this methodology by considering one of the problem. Now, this problem is exactly related to a simply supported beam and consider with eccentric point load. Let us see here, a beam of length 6 meters is simply supported at its ends and carries a point load of 40 kilonewtons at a distance of 4 meters from the left support. Yes, is the eccentric load. The toward the span is 6 meters. And this 40 kilonewtons is acting where? At a distance of 4 meters from left support. And it is 40 kilonewtons, huge amount. Find the deflection from right support is 2 meters. Find the deflection under the load and maximum deflection. Yes, find the deflection under the load. Suppose point A, suppose point B, support B, and at point C. We want deflection under the load, that is YC, and also maximum deflection. Also calculate the point. Also calculate the point at which maximum deflection takes place. Given moment of inertia of the beam is 7.33 into 10 power 7 millimeter power 4, and modulus of elasticity is 2 into 10 power 4 Newton per square millimeter. Alright. Now how to apply? This is the same case we have already derived in before case study. So we can directly substitute if we remember the formula. Otherwise we have to go for the calculating the bending moment equations. Those type of problems we will see in the further sections, coming sessions. Now the span of the beam is 6 meters, that is 6000 millimeter. And W equal to 40 kilonewtons. 1 kilonewton equal to 1000 newtons. So 40,000 newtons. Now distance of point load from the left support A equal to 4 meters, and that is A equal to 4, and right support B. This is A and it is B equal to 2 meters. Now deflection under the load, that is a deflection under the load, that is point C, YC equal to, we derived the formula, that is YC equal to W times A square B square by 3I times L. Substitute A value, value of the A, value of the B, value of E, value of I and L, all are unknown values. The unknown YC can be calculated. The calculated value of the YC deflection is negative 9.7 millimeters. Why it is negative? The significance of negative is here, the downward deflection. Now that is the downward deflection. Okay. So by using those values, we can calculate the maximum deflections, and here all calculated here under the load and maximum deflections. So we can substitute and we can get it directly, the deflection formula, deflections we can calculate. Like that we can calculate the derived, by using the derived formula, we can, by substituting directly all known values, then we can get it the maximum deflections, etc. Now coming to next problem. A beam of length 6 meters is simply supported at its ends and carries 2 point loads 48 kilonewtons and 40 kilonewtons at a distance of 1 meters and 3 meters respectively from the left support. Find deflection under each load. Next, maximum deflection, and also the point at which maximum deflection occurs. So here the modulus of elasticity, that is E equal to 2 into 10 power 5 Newton per square millimeter, and I equal to 85 times 10 power 6 millimeter per 4. So how to calculate here? This is the problem they have given. That is 1 meter 48 kilonewtons and another one is 40 kilonewtons at 3 meters. And here supports A and B is a completely point loads at a distance of 1 meters and 3 meters from left support A. The span of the beam, what is the span of the beam? Here it is 6 meters. Now by using the sign conventions of shear force and bending moment concepts, we have to calculate the reactions at support A and support B. The calculated reaction, the values of support A and support B are here. At support B 28 kilonewtons calculated value, and support A it is 60 kilonewtons. So the reaction at A is more than the reaction at B. Alright. Now what to do? Let's take a part at the distance of X, such a way that you consider the distance of X from support A between point D and point B. D and B, if we consider, this equation involves the variation of the slope and deflection throughout the span of the beam. That's why we consider section X at a distance between D and DB. If we consider the section X between C and D, we can calculate the deflection and the slope of points up to C and A. We can calculate theta C, YC. theta A and Ya. We can't calculate theta D and YD. We can't. It can't be calculated provided if we consider the section from between C and D. So we want C and D. Where is the equation involves? This equation X between DB, this involves theta A can be calculated, theta B also can be calculated, theta A can be, theta D can be calculated, theta C can be calculated, YA, YC and YD also can be calculated provided if we consider the distance from left support is at a distance of X, okay, from left support. So this is the way. Now we consider mx. Now at a distance x equate to directly our equation varying the bending moment equation, that is ei times d square by dx square equal to RA times x minus 48 times x minus 1 minus 40 minus x minus 3. This RAX for part 1, this 48 times x minus 1, sum of these two up to part 2 total through the span of the beam. Now if we integrate, RA means that RA considers 60, value calculated 60 times x minus 48 times x minus 1 minus 40 times x minus 3. So we'll continue like that. Then after simplification, yeah, this is you can simplify it. The deflection equation, that is I times dy by dx minus 60 times x square by 2 plus C1 minus 48 times x minus 1 square by 2 minus 40 times x minus 3 by 2. This equation gives the slope equation, and again integrating the deflection, this slope equation once more, that gives the deflection equation. So this, after that we have to find out the constant of integrations by using two boundary conditions and substituting these C1, C2 back in equation 1 and 2. Those equations are considered as a slope and deflection equations. So like that we have to solve the given objectives can be solved. The given objectives are deflection under each load, maximum deflection, and the point at which maximum deflection occurs. We can continue this problem in the next session. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.